Okay. Whoa, sorry. I'm sorry for starting late. IT threw me a curveball and re-imaged the computer over Christmas break, so I was not logged in and had to reset everything back up. Rookie mistake, I guess. Welcome to Phys 2. If you had me last semester, welcome back from Phys 1. If you haven't had me yet, we'll get to know each other over the course of the next semester. I'm looking forward to seeing some familiar faces. I'm also looking forward intro physics is a lot of fun. There's a lot of things that we have to learn over the course of the semester. Granted, we have 3 semesters, so a lot of things that we're trying to cram in over the last, 6,000 years that we've learned about how the universe works and the like. Phys 2, we're going to mostly start in electromagnetic theory. We're going to start with electrostatics, get into magnetostatics, get into a little bit of dynamics on both of those. And by the end of the semester, we'll wrap things up with a nice review from chemistry on the thermo that you did probably in intro chemistry and physical science in high school and the like. My name is Will Waldron. I have been teaching here. This is my second semester, I should say. And it's been a good move here so far. My wife and I met in Huntsville, Alabama. We ended up moving to Arkansas to teach at Harding University back in 2019. Again, rookie mistake, considering I agreed to start teaching with no prior teaching experience in 2019, and all of a sudden the world shut down in 2020. So I was not only learning how to teach, I was learning how to teach online, and all that other fun stuff was going on. So we have 3 kids, Isaiah, Jonathan, and Brooklyn. Isaiah is about to be 4, Jonathan is about 2.5, and Brooklyn is about 10 months right now. I did my undergrad at Harding University, where I was teaching previously, and did my graduate work here, my master's and PhD. My dissertation was quantifying ram pressure stripping effects using the Hubble Space Telescope. That's what I can remember about it. I don't even remember the title of my dissertation at this point, and that was only 2.5 years ago. I worked at Dynetics before it was Leidos, so I left in 2019, and they got bought by Leidos in December of 2019. I enjoy just walking in the woods. In fact, the day before my comprehensive exam in physics here as a grad student, instead of studying that day, I took my hammock to Rainbow Mountain, started reading a book. I think I got like 3 pages in and I fell asleep for like most of the day. It's just a good way to relax. I do like to play Minecraft. 3 kids later is a lot more difficult to play Minecraft, but when I find time, I jump into my world and try to work on it. I just started a new one because my old one was so old and I didn't want to update and lose things. I waste many turns on Civ 6. I like bush hogging, again, the theme of being outside. I've told previous classes, if you had me last semester, I know you get frustrated with me and your other professors. Sometimes professors just need an outlet too. To me, bush hogging, taking a massive piece of metal and knocking down trees in the front field of our house in Arkansas, taking the front end loader and digging a tree up by its roots like the sweet gums that take over. There's just something very cathartic about that. It's nerdy, I know, but I love a good coding assignment in Python. I just enjoy, if you've ever seen XKCD comics, I'll use them quite a bit in this class. One of my favorite XKCD comics is, hey, you're flying, how are you flying? Oh, it's easy. With Python, you just import anti-gravity and the rest is taken care of. Like, programming's fun again. So I enjoy that. Maybe you enjoy it, maybe you don't. I'm curious, based on my background, my favorite games or anything like that, are there any questions about me that I can answer now, just so we can get to know one another better before we dive into the main content for the day? Yeah, what's up, Maggie? Casual. I just picked up a brand new video game over Christmas. Bluey, the video game. Again, so those levels of games I'm all about. We also got Paw Patrol, which is a bit intense for me. Like, there's a lot more problem solving and puzzle solving. But Bluey, man, you just walk around the house and you find things, and I get to waste 30 minutes with my sons. Brooklyn's not old enough yet, but she'll get there, I'm sure. But Bluey has been a great, great new video game since Christmas. Yeah, up here. Can you make a Physics 2 Minecraft server? A Physics 2 Minecraft server? Sure. I mean, if you have a place to host it, I think that would be a lot of fun. And you just hop on Discord and the Minecraft world, and y'all can solve physics problems together. We've already done projectile motion, but when we get to circuits, like you can build logic gates with redstone and all that kind of stuff. You know, easy, easy peasy. Anything else? It's okay. This is a huge class of nearly 200 people. Just another professor. It's funny to me when professors when students can't remember my name, and it's like week 8 or 9, and it's like, yeah, I get it. There's a lot going on. But we'll get to know each other. I make a lot of really corny jokes, probably excessively so. That'll come out, I don't know. We could make this class really boring. Nobody wants that, so I try to at least have a little bit of levity with it. I don't know, bring the yeast, I guess. So I'd like to get to know you guys. Again, I know I've had some of y'all a little bit, but if you scan the QR code, if you didn't, you can go to menti.com and use the code at the top of the screen there. But I'm curious to know, I'm guessing the majority of you guys are mechanical and electrical engineers, maybe some systems engineers, chemical engineers, math. There's always someone who abbreviates the engineering, so we've got someone who's majoring in E. We usually have someone who's majoring in me. Someone's majoring in fun, aerospace. A German major in here? I think you're in the wrong class. Or maybe you're double majoring, I don't know. Beer and girls, yeah, there's always one student. Always one. Okay, cool stuff. Aerospace, mechanical, not surprising by any of those. What year are most of you guys? I'm guessing most of y'all are freshman, sophomore. Okay, mostly sophomore. I never know, because I think right now with the normal engineering timeline, we're kind of out of sync with what is normally done. So I think the normal timeline, you begin on the spring of your freshman year or something. So I don't know. I'm just here to teach the class, but it is good to know that this, for most of you, is not your first semester in college, I'm guessing. Favorite hobbies. Beer and girls does not count. You already put that as a major. I guess your major could be your hobby. I don't know. Video games. Storm chasing. Yeah, when I was teaching at Harding, that never showed up on my list. I can tell you that. What was that? Yeah, somebody with swirl is in here. That's right. Motorcycle, hunting, Magic the Gathering, guitar, video games. Yeah, that's much like previous semesters and at Harding too. Video games went out, reading, hiking, gaming, Python scripts. All right, someone after my own heart. Python scripts is up there on the bottom left. I appreciate that. I heard that. So how you feeling about this course? I think some of you had me, some of you didn't. The first one up was all ones. Strongly disagree. That's not a great place to start. Or you just hit submit without doing anything. All right. Yeah, difficulty, mostly neutral, agree or disagree, mathematically prepared. We'll work on that. There's going to be a little bit of brushing up that we do. Every new concept that we come to is going to stretch you a little bit in terms of the mathematics that we need to do, to use. Expect to do well. I hope we can work together. For those of you who are more in the middle of you expect to do well, my office hours are posted on the syllabus, they're posted on Canvas, they're posted as many places as I can think to have it. We usually have to move out to the physics common area up here in the optics building, just because with 6 of you, I can't fit you all in my office and there's not enough board space. But y'all are welcome to come to my office hours. Not pointing any fingers, but one of the students in this class said I seemed super intimidating last semester because I yell a lot when I lecture. Truth, I yell a lot when I lecture, but it's not out of anger. It's just because I get really, really excited about things, and in my excitement, I tend to go really, really fast. But all that to say, like, please, office hours are for you guys. Feel free to come to that. I would love to meet you. In fact, that's how I get to know the majority of you is through those office hour visits. So let's talk a little bit about the syllabus. The syllabus, let's see here. Can I go to full screen mode here? Yes, I can. And let's get rid of that. Dismiss. Hi, Ethan Burks. Welcome to the syllabus. So again, my name is Dr. Will Waldron. I got my PhD here. If you just call me Waldron, that's fine by me, Professor. If you call me Professor, I prefer to go by Professor Dumbledore, but be that as it may. My office, if you go out this top left or your right door, it will take you into the optics building. Take a left on the first hallway you come to. I'm at the very back end of that hallway in optics building 238. My email address is there. A brief note about my email address. If at all possible, use Canvas inbox to message me about this class. I like to keep my research and professional stuff on the email and my class-related stuff in the Canvas. My office number, that was on the template, so it's there. Not that I expect many of you to use phones at this point. If you click this link, it will take you to a Google Calendar link where you can see my office hours. It's set up like if you've ever used You Can Book Me, same kind of thing. You don't have to book me on that link to come visit my office hours. You can just pop in during office hours. I will say, if you want to look at that link, though, whether on Canvas or anything else, it's worth taking a note of the hours on there because they may change. Like something might pop up, a kid gets sick or something, and the hours will always be up to date in terms of my availability on that link. The final exam, in case there's always one, is Tuesday, April 29th from 11:30 to 2 p.m. We'll address that closer to the end of the course. This is an in-person class. It's spring 25. We're going to cover electromagnetic fields for 2/3 of the semester, then wrap it up with thermo. You should have, whether through the Charger course pack or through your own Amazon purchase or something, Tipler and Muska's Physics for Scientists and Engineers, the Macmillan 6th edition, published in 2020. You'll also need access to Achieve. This is something, if you had me last semester, that is different. I'm not using iClicker for attendance because it was just difficult to integrate. People forgot. And we're not using Scantrons for exams going forward. You should have, if you've taken chemistry previously, one of those turning point clickers. Hopefully you have a license for that, and you can, if you've already gotten rid of your clicker, you can go get one from the bookstore, you can buy another one used. Make sure that you have a license, a subscription, whatever it is, to the clicker. You can use the app on your phone for the attendance portion of it, but it has to be the physical clicker for the exams. So just know that if you've taken chemistry here, it's the same kind of deal. Instead of Scantron, you're going to have clickers for the exams, so that way I don't have to run them over to the other building. I don't have to keep up with all of those. I don't have to worry about whether you put it in the right box or anything like that. We're just going to be using the Turning Point Solutions clickers. I didn't do attendance today because I wanted to cover all of that first. Does attendance require a license? I do not know. I will find out about that. Let me write that, or send me an email and I'll look that up. I'm planning on sending a summary of like all of this initial stuff tomorrow.
When is the first time you're going to check attendance?
On Tuesday, hopefully, if for some reason it's not still icy or anything like that. But yeah, hopefully Tuesday we will start using this for attendance, using Point Solutions Clicker, the app for attendance. Yep. To register for Point Solutions? Yes, I was sent instructions, but the integrations were not visible on my Canvas page. So I was hoping to have that out before class today. A little link and video and registration guide. Didn't get that yet, but hopefully I will soon as ETLC opens that up for me. Yes, what's up? What? Yes. Grayson is pulling on a theme that popped up a lot last semester. Again, if you didn't have me, sorry, I guess inside joke with the previous class. I am 33 years old now, and the previous Phys 1 class made excessive points to indicate that that is old in comparison to many of you guys. Okay, so be it. It's true, y'all are in your early 20s, most of you, late teens. Yeah, to me, I'm almost double your age, I guess. I don't feel that old. I would go skiing tomorrow if there was a great place to go do that and fall and get back up again. Resident old guy, sure. I'm fine with resident old guy. I was just told recently that I've always had the spirit of someone that's probably 40 years my senior. So sure. We'll be using, I need to get rid of this statement on iClicker. We'll be using Canvas. Everything's through Canvas. Just stay connected through Canvas. Make sure your Canvas notifications are set up to go to your email or push through the app or something along those lines. Homework, I've changed that since last semester, is 35% of your grade. The little video quizzes that you watch beforehand and answer a few questions, those are 10% of your grade. The exams are 35% of your grade. The big question that students even want to know on the day one, what are exams going to look like? If you haven't had me, exams are going to be 30 questions, give or take, and they're going to all be multiple choice. It's going to be two-thirds of the exam are going to be factual, conceptual questions, multiple choice, and 1/3 of the exam is going to be numerical problem solving, but it's all multiple choice, just for simplicity of grading and simplicity of writing the exam. The final exam will be very much the same with the exception that it is only factual conceptual. We'll be doing problems in class, but those will not be graded. The little quizzes you'll find with Menti, that interactive presentation software I use, I'll throw questions at you as we go while I lecture, but those are anonymous, first of all, and second, I don't grade them. Missed assignments, homework, please hear this because I had too many people email me at the end of last semester about this. My homework, I know there are other professors who the homework cuts off on the due date. My homework is open for a week after the due date with a cumulative late penalty. So if you miss the due date, you can work on it the next day and you'll get a 10% hit, the next day a 20% hit, the next day a 30% hit, up until a week, at which point it does cut off. The video quizzes, those cut off at the due date. Video quizzes cut off at the due date. Homework cuts off a week after the due date. Attendance policy, come to class. You're paying for it. Someone's paying for it. It's a good thing to be in. I can't help you if you're not here. Again, please communicate with me through Canvas. I'll communicate to you via Canvas announcements. For example, today at 4 o'clock, I'm supposed to drive to East Tennessee for a wedding. It's supposed to snow tomorrow. I don't know. I'm hoping I will be back in Huntsville by Monday or Tuesday. If I'm not, I will tell you via Canvas and we'll pivot to online and figure something out. My general policy, if we pivot to online because of snow, especially for the traditional college students in here, if you want to have a big, massive snowball fight on the quad or cozy up with your blanket and a mocha on your couch or whatever, like everything I do is recorded, including the online days. If you choose to have a snowball fight while I'm having class online, I would have probably done that too as a student. So I get it. I'm not offended. You can watch the recording later. I will not take attendance if we pivot to online. It's just going to be something where to answer questions, to stay on track for the course, I pivot to online in any weather event. I will announce that through Canvas. I tend to use, because we're a Google campus, I tend to use Google Meet for my online sessions, and so I will post that in the announcement, a link for you to log on to Google Meet. I will try to make it as abundantly clear as possible, because again, there are nearly 200 of you in here. There are nearly 200 in my other class. I don't want to get 400 emails trying to clarify everything, so I will do my best to make it abundantly clear about what we'll do via Canvas announcements. Don't cheat. Don't cheat. It's never fun to deal with. If you are interested, if you're the person type A to the max, you want to know exactly what we're going to be doing every day. This is a tentative daily schedule. It's here in the syllabus. You can also click this link and it will take you to the Google Sheets view of this very same schedule. I've seen through the accommodations office many emails about accommodations for you guys. If there's something you feel like you need to talk to me about, I'm more than willing to hear about it. I have dyslexia, I get it. Like, it's nice to have time and a half. I will work with you as best I can to accommodate you. Yeah, I think that's mostly everything. Why does it keep logging out? That's frustrating. And by the way, if you're new to my class, anytime I link something on the Menti page, you can click that link on your own devices and it will take you to it will help you follow that link. Communication and due dates are on Canvas. I have already posted, because if you had me for Phys 1 last semester, I was building the course as we went. Fortunately for you, I was also teaching Phys 2 at the same time. Everything for the entire semester, as far as I'm aware of things that I want to have on there, is already on Canvas. If you want to go home tonight and knock out every single homework and video quiz between now and the end of the semester, that is your prerogative. Have fun. Yes, ma'am.
Phys 2 is harder than Phys 1?
So a lot of the electricals like Phys 2 better than Phys 1 because it's the basis behind what they do. For the ones who are not electrical, people don't like the EMAG portion near as much and do find it difficult. But then the thermo comes in to save the day at the end, and it tends to be a breath of fresh air for most students that I talk to. So yeah, the EMAG portion can be frustrating. It will be valuable to you to print off from the internet one of those signs that you hang on your door that says "Bang Head Here." It works. We had one at Dynetics. We had one at Harding. There's something about it. But yeah, I hope that we can work together though and make this all abundantly clear. I know this is a huge class, but it also depends on you guys to make me pause and ask me questions, which I welcome in class, because EMAG is incredibly abstract. Like most people, the first time we start talking about electric fields, like, so there's a farmer and he's got like a electric fence or something like that, an electric field, and it's just, we're not used to thinking in these abstract terms. And so if you know anything about mind palaces or something, like, there's a lot of building and framing that we're gonna have to do for this semester, but it's a lot of fun. Fortunately, I used some of these, I think last semester in Phys 1, but in Phys 2 there are, write this down in your notes if you're an interactive person, which there's valuable for any learner to do interactive. But PHET, P-H-E-T, a lot of the stuff that we're going to be doing, and I'll start linking these in Canvas. I started doing that yesterday, but didn't get a lot of them. But PhET has, if you start getting into the middle of all this and you're like, I still don't know what an electric field is, and we've been talking about it for 3 weeks. PhET has great demonstrations where you can drop charges in and see electric fields. And to me, like, even after taking it through grad school, like, those interactive presentations were a lot of the things that helped me build up my own framework on the matter in electromagnetic theory. You'll need a Tipler textbook and Achieve. I meant to take off SIMPHI. We won't be using SIMPHI in this class, but you'll need it for the lab. The first lab week, I think, you may want to check your schedule. Dr. Cronus said it was the week of 127, so I don't think there's lab this week or next week, but then the next week there's lab. There are no makeup for missed due dates on exams. That is for unexcused absences. For an excused absence, email me ahead of time. I just need to know that you're sick or whatever it may be. Generally, what will happen is if an exam is on a Tuesday, the makeup day will be the following Friday, and if an exam is on a Thursday, the makeup day will be on the following Monday. Otherwise, we will try to get you in the testing lab, but that's got its own frustrations. Last thing, if you have a clicker or don't have a clicker, you'll need one of these 3 versions of clickers. The one that I've been playing with is this one on the bottom right. I don't know which one it is. Make sure you register online. Yes, per the question earlier, I'll try to have registration guidelines posted at least by tomorrow on that. We'll use the phone app for attendance and the clicker for exams. Sorry, I'm from Murfreesboro, Tennessee, so sometimes my southern comes out. Yes? It should come with the Charger course pack, and if you opt out of that, you have the option to buy the book without Achieve or buy the book with Achieve. You'll want it with Achieve, and basically what will happen, that actually is a great little segue here. Let me pull up my other web browser here. So this is the course landing page. I organize everything by modules. I know from working with students for 7 years now, you look at you look at this on the first page and then you use the calendar for the rest of the semester. That's fine. If you do that, you're missing like tens to hundreds of resources that I have prepared in advance for you for your own success in this class. So please occasionally visit the homepage and look at the modules for each one of the courses that we're doing. For each one of the units that we're doing. So first things first, you can come in and you can look at the welcome, how to navigate this course, more information about me. There are links to the course syllabus, the tentative schedule, and this is where you will want to land. You'll need a license key, which you should have. Go to student registration, start here. It will link you into my Achieve section in their system. And then from there on out, all you have to do is click on the homework or the video quiz link, and it will dump you into their system, and it will pull your grade in. Another question that I got weekly from different students last semester about Achieve. Achieve syncs grades like every 4 hours or something like that. So if you start a homework and you hit a grade sync after you've only answered one question, and it says you have 1 out of 10 points on the assignment, but you know you finished the rest of the assignment, don't email me. Wait 24 hours for the grades to roll back to Canvas, and then if there's still a problem, then we'll address it. But if you see that you have a 1 out of 10, but you know you got 98% on all of the problems on Achieve, it'll just take a little bit of time to get there. The Student Resources tab, again, I've got my office hours again on there. UAH posted basic needs. If you have food insecurity or something else, mental health needs, there's a great resource there. Another great resource is, we're not using it because they're still building up. The textbook is great, their problem set is not, in my opinion, but OpenStax is a free online textbook for this course, University Physics 2, as it's called at a lot of other universities. So you can go to their reading and note-taking guide, their time management guide, and I've got links to their specific sections going out through the rest of this course. But OpenStax is a great way if you want to read our textbook, you don't like it, you go to OpenStax. They've also got videos that you can use. Here's the link to the OpenStax physics textbook. Here's the link to the Khan Academy physics library. They've got great resources as well. There is a practice assignment. This will be in my first day summary announcement that I put in Canvas tomorrow. The practice assignment, if you don't do it, will show up as a 0 in Achieve, but it does not roll into the Canvas gradebook. It's just for you, if you've never used Achieve before, to know how Achieve works, how to insert problems and the like. If you find yourself a bit rusty on algebra, trig, or calculus, you can go to any one of those modules. There are no assignments in there. It's just links to things that I deem valuable for your success in this course. The first real one where we actually have information here that you might need is this Unit 1, Electric Charges and Fields. You'll see that all the slide decks that I use are on that first link. The problems that we solve in class are going to be at the second link. And the equation sheet, which you may use from day one and will be on the exam, is there on the third link, Unit 1 equation sheet. That will be the structure of every subsequent module. From there, you've got all of your different homeworks and pre-lecture quizzes and so on and so forth, with the exam showing you tentatively what the date of our first exam will be and the second exam and the like. The syllabus, I think a lot of folks copy and paste their syllabus onto here. I don't like having to keep up with two different syllabi and make sure they're consistent, so this just links you back to the Google Drive version that I showed you previously. If you miss a class, or if you were in class but you were confused on a topic, you can go to the Panopto tab. That's where you can find the recording for each day. You can see the one for today is there, but it usually takes about 15 minutes to process after class. But that way, if you were confused about something and want to revisit something after class, you can go there to Panopto. Pardon?
For those 3 clicker options you gave us, like, did anyone have pros or cons? Is one of them better than the other?
I do not know of pros or cons, one better than the other. I just know that the ones that I showed you are the ones that are compatible with the receiver that I have. And any of these work because I'm only going to be asking you multiple choice questions anyway. So for example, with this one, this just has multiple choice options. These both have a QWERTY keyboard and you can put in the multiple choice. So if the answer was B, you could click this one here, or you could put in B, wherever it is, B on your clicker here. But any of those 3 would work. Any other questions about the syllabus, about Canvas? Yes? The bookstore has clickers and licenses as well. You'll need the clicker and the subscription. And I have no idea. I should know that, but I don't know. All right. The day is still young, and we have much more to do. So, everything begins with this second semester of physics based off the idea that there is something called charge. What is charge? What would you guys say is electric charge? Yeah, up here. Yeah. So right out the gate, hit the nail on the head if you didn't hear what was said. It is a fundamental property that matter has, that particles have, and it's going to either be positive or negative. And while what he said is true and is more or less what I was going to say, it's also one of the frustrating things about physics. Like I was just reading before I walked into class, the 2000 millennial open questions in physics. And some of the open questions in physics dive into exactly what was just said. And that is, but why are there these fundamental things? And what are the fundamental things? And why are the fundamental things the fundamental? Like, for example, I could ask you the same question, what is mass? And we get into a chicken and the egg. If it's completely classical arguments, you say, well, mass is something that measures inertia. And I say, well, how do you measure inertia? Well, it's based on how much mass you have. And another comment? It's okay. So charge is one of those things as well. Charge is almost frustratingly so something that is hard to define, easy to measure. I mean, I say easy to measure. If I ask you to go out here to where there's drywall, maybe not these stones on the wall, and have you rub the back of your head up against the wall, your hair is going to stand up after you rub your head on the back of the wall. Not to mention all the other people taking classes in this building wondering what you're doing in the first place. But we know that there's this repulsive element to like charges, for example. So Scientifica Britannica calls it charge is a basic property of matter carried by some elementary particles that governs how particles are affected by the electric or magnetic field. Well, as we're going to talk about, again, this is a bit of a frustrating definition because one of the things that we ask ourselves after learning what an electromagnetic field is where do they come from? Well, electromagnetic fields come from charges. Okay, great. Charges interact with it's frustrating. And if you have the secrets to life, the universe, and everything, as far as I know, it's 42. But other than that, if you've got something a little bit more helpful in terms of this material, that would be most helpful. A bit of history. So our current understanding of charge goes back about the time of Benjamin Franklin. So you've got this idea that at the time that charge behaves a lot like a fluid. And you've got this fluid is going to transfer between objects, but then you've got these, you can rub silk onto glass and it charges the glass one way, or you can rub fur onto rubber and it's going to charge the rubber one way, and you've got all of these different interactions here, and basically what was thought is that you've got some negative juice and some positive juice or something along those lines, and they interact with one another or flow between one another. We now understand that there are, yes, positive charge carriers and negative charge carriers, but thanks to Benjamin Franklin getting it backwards 250 years ago, the thing that moves, the charge carrier that moves, that makes things appear charged, is the negatively charged particle, the electron, for example. So if you have something that's positively charged, it has fewer, or it's lost electrons in some way. And if you have something that's negatively charged, then it has gained an excess of electrons in some way. And he was able to determine that, okay, if I rub fur onto hard rubber, then they end up wanting to repel one another. If I bring in that this second rubber rod here, then what ends up happening is this one dangling from the string is going to want to start rotating clockwise. Whereas if I rub silk onto glass, then what happens is I end up getting a repulsion as well. But then if I bring the rubber near the glass, I get an attraction between those two. And so the earliest understanding that like things repel one another and opposite things attract one another became instilled even as far back as 250-ish years ago. Which, if you're an electrical engineer, you might identify with this next comment. comic. Again, it comes from XKCD. But if an electrical engineer gets hold of a time machine, you can expect the first thing they'll do is have Benjamin Franklin reverse the sign. The one on the glass is negative, not positive. So that way, electrons would be positively charged, and that's going to be what's moving and carrying the charge for us. And you say, wow, how could electrons be positive? It's just convention. Like if you could go back and change this right now, you would think it absurd that electrons would be negatively charged. So you have a mission if you ever create a time machine. Forget Arnold Schwarzenegger and Terminator and that kind of stuff. So later on, we have the Millikan oil drop experiment, which was a fun one to use at Harding. I don't know if we have one here or not, but the most important takeaway about the Millikan oil drop experiment is that this thing that measures charge is something that is fundamentally quantized. What does quantized mean? Yeah, back here at the top. Yeah. So you might hear a mathematician say instead of distinct, they would use the very specific word discrete. Rather than being continuous, you only get a certain you only get a certain multiple of this fundamental charge, which is 1.602176634 times 10 to the minus 19 coulombs. Coulombs there, you should take note of, is the standard SI unit of charge. And so if you want to know the total charge or the net charge on any object, the net charge, which is represented below as uppercase Q, is going to be equal to plus or minus some number, just some number, 1, 2, a mole, whatever, times E, where E is the elementary charge. Now here's a common mistake that is made in intro physics. You see E and you assume it's the charge of an electron, and so you assume that it has to be negative. But E, we just are concerned about the magnitude of that little e right there, and the magnitude of that little e is known as the elementary charge. And both protons and electrons have the same magnitude of charge. Protons just happen to be positive, electrons negative. Yes, Maggie?
Is net charge almost always going to be used as a Q for the variable?
Q, uppercase or lowercase q. Q tends to be the main variable we use, either uppercase or lowercase for charge. Big Q, not even as a rule of thumb, I would just say like loosely big Q is going to be a macroscopic amount of charge, like microcoulombs or greater, like micromilli whole coulombs, and anything below that would be little q. But frustratingly, you'll see me solve problems, you'll see problems in Achieve that don't follow that convention. But Q, the letter itself, tends to measure or be the variable we use for charge. Now bear in mind that this net charge, how can I say this, does not necessarily correspond to the total number of charge carriers within an object. What I mean by that is, if you take my briefcase, for example, my briefcase more than likely has a net charge of around 0. Right? There is 0 net charge between the protons and electrons on my briefcase. But that does not mean that there are 0 protons and electrons that make up my briefcase. In fact, if there's matter there whatsoever, there have to be protons, and if the charge is neutral, then what that means is for every proton that makes up my bag, let's say it's 5 moles of leather proton material, But 5 moles of protons, if the net charge is 0, then that means I have to have 5 moles exactly of electrons as well. So net charge just determines the excess using, or I should say this equation here is just used for determining the excess number of electrons. Excess would mean big Q is positive or negative. If I have excess electrons, it would be negative. And if I have a deficiency of electrons, then the net charge would be positive. A deficiency would be positive, so that means I've got more protons than electrons, more positive charge winning out over the negative charge. Yes. So, an object carries a charge of negative 50 nanocoulombs. How many excess electrons, so using that previous equation, how many excess electrons does this object contain? Oh, it says responding is off. Press C to allow responses. All right. This is what I expected. It's day 1 and people aren't ready for crunching math yet. The net number of electrons at this point is going to be roughly 3 times 10 to the 11 excess electrons. And so we get to this case here of, okay, negative 50 nanocoulombs. And you said that there are 50 excess electrons, but an electron does not have a charge of 1 nanocoulomb. An electron has a charge of the elementary charge, 1.602 times 10, 1.602, times 10 to the minus 19 coulombs. So if you want to find how many there are, let's come down here and start playing around with this. So I've got big Q, the net charge. This was the minus 50 nanocoulombs. So minus 50 times 10 to the minus 9 coulombs. If you're not familiar with your SI prefixes, especially the little ones, we're going to be using micro, nano, femto, pico. We're going to be using those a lot this semester, so it would be worth your time to brush up on those. And then that's going to be times n, is equal to n times the charge of the carrier, which in this case is going to be the charge of an electron, which is negative the elementary charge, so minus 1.602 times 10 to the minus 19 coulombs. So now if I want to know n is going to be Q over minus E. So that's minus 50 times 10 to the minus 9 coulombs divided by minus 1.602 times 10 to the minus 19 coulombs. And from there, that should give you that 3.12 times 10 to the 11 excess electrons. So almost a trillion excess electrons. You think, my goodness, that's crazy. But, I mean, there's probably roughly 10 to the 80, 10 to the 85 particles in the universe, so we're barely scratching the top of the barrel with a trillion here. We have a long way to go. No, it's not the charge of anything. It is the smallest possible charge that we are able to measure on a macro scale. So protons are going to have a charge equal to plus 1.602 times 10 to the minus 19 coulombs. And electrons are going to have a charge of minus 1.602 times 10 to the minus 19 coulombs. But for example, like this arbitrary sphere that I had, it didn't have a charge of one of those two things. It had a charge of 50 nanocoulombs, or negative 50 nanocoulombs, right? So charge can be any multiple of those two numbers right there. If you're talking about elementary particles, with the exception of quarks, they're going to have either of those two charges or zero. Your elementary charges, I don't know all of the standard particles, but the quarks end up having either 1/3 or 2/3 of that multiple, and then some of the other ones are either uncharged or have an integer multiple of that number. But the only elementary particles that we're going to be working with that carry charge are protons and electrons. Yes. So Grayson's question was, okay, this question explicitly stated that we had an excess of electrons. But what happens if this explicit statement of excess electrons was not there? To drive the point home, he said, the negative 50 nanocoulombs, the negative sign there means you have excess negative charge, which means you're going to have more negative charge carriers present than positive charge carriers, meaning electrons. Yes. All right. Now, a brief note that will come more, especially for the physics majors later, if you go on to study physics in graduate school, but it's still important to note that charge is conserved. In any interaction that we've seen, as far as we can tell, charge is conserved. So if you start something with positive net charge, and you go through some sort of interaction, then the total system should have that same net charge at the end of that interaction. Where that comes down to you guys, especially say in the lab, and you have an object, say some sort of metallic sphere, that has 1 nanocoulomb of charge on it, plus 1 nanocoulomb of charge, and the other one, another metallic sphere that is neutral. Between the two of them, there is the 1 nanocoulomb of charge. And if I bring them together, we'll talk about conductors here in a second, but the charge should distribute equally between them. But since charge is conserved, the remaining charge after the two spheres interact with one another should total to 1 nanocoulomb of charge, which is what I started with to begin with. So this is called, the net charge between two objects remains constant. This is called the law of conservation of charge. All right. So conductors and insulators. Of course, you can talk about this if you're a mechanic. Question? Grayson's question was, let's say it's just a mostly isolated sphere. There's not a second object present. Can an object leak charge? There is something called electrostatic breakdown, where charge can arc off of something, but that charge has to go somewhere. For example, I should say in addition, in the South, one of the reasons that we do electric at the beginning of the semester when it's cold is you'll see if you go into the lab during the middle of summer here in the South United States, you could measure the charge on an object to be 1 nanocoulomb. And then a minute later, it's 0.9 nanocoulomb and 0.8 nanocoulomb, 0.7 nanocoulomb. And you see the charge draining off, even though the sphere is isolated. It's a metallic sphere, and it's resting on an insulating stand. Does anybody know where that charge goes in the middle of the deep South in the summer? What's that? Humidity, yeah. So there's water vapor in the air, and water vapor actually is really good at accepting excess charge. And so as the high Huntsville humidity passes over, it will pull charge off of that onto the H2O molecules. So yeah, but generally, even still, the charge it didn't disappear. It just got passed off to the H2O molecules. You can have different weak interaction decays. Like, for example, an isolated neutron can break down into a proton and electron pair and antineutrino, I think is what it is. But if you have a neutron that has zero charge decay into a proton and electron, well, +1 elementary charge and -1 elementary charge, the net charge after that weak interaction is still 0 net charge.
Is that how lightning ends up happening if the H2 molecule just absorbs a bunch of excess charge and then difference?
Lightning, I'm sure there's, I'm guessing there's a way that lightning could be aided by excess charge in the actual water vapor, but from what I understand, it has to actually deal with or at least cloud to ground lightning is a difference in localized charge between the cloud and the area on the ground. And so that's where you get that breakdown, right? But cloud to cloud lightning, I have no idea. I would go across the street to our partners in atmospheric science. Philip Bitzer, he's a lightning guy, Dr. Bitzer. And his background's in physics. All right. So we have conductors and insulators. The question that's going to pop up that I backed off really quickly, but mostly I just felt like it wasn't a well-worded question. The main difference between conductors and insulators when we're talking about electrical properties is conductors, excuse me, my voice still changing after 16 years. Conductors allow charge to move freely. Insulators do not allow charge to move freely. Conductors allow charges to move freely. In fact, I think if I skip this page, no. Okay, I'll just show the correct answer here. Conductors allow electric charges to move freely, the one that's checked up there. Thank you. While insulators do not. But that does not mean that insulators cannot carry a charge. Right? The classical example of an insulator that can carry charge is instead of rubbing your head on the wall, you rub the balloon on your head. The balloon is rubber, it's an insulator, but you rub it on your head and then you stick that balloon onto the wall and it's going to stay there. The balloon is an insulator, but it can still hold charge. The one difference is where you rub the balloon on your head, that's where the excess charge is going to stay until it leaks off into the air. But it's going to stay in that one spot where you rubbed it up against your head. Here's an interesting question, though. You rub your balloon on your head, so you have created some localized net charge, non-zero net charge on the balloon. But as far as we know, and we would assume, the wall is electrically neutral, right? Like you don't see anything being electrically attracted to that wall over there. So how is it I can take a positively charged balloon, or at least a balloon that has a region of positive charge on it, and get it to stick to a neutral wall? Okay, yes, that was right. So what was suggested was maybe it repels the positive charge. So come back to where we began this discussion, and that's that like charges repel and opposite charges attract. And so the rubber balloon is an insulator. The wall is an insulator. So where is the charge going if charge is not allowed to move freely, such that the positive balloon can still repel the positive charge on the wall and attract the negative charge? Like, where does the charge move if it's not allowed to move freely? He's right. He's on the right track. So this gets down to the heart of what I mean by charge moving freely. Conductors, let's say most metals, for example, conductors allow an electron to hop between adjacent atoms, right? So let's say you've got some sort of solid, it's made up of 10 atoms, some sort of lattice of 10 atoms, and the electron begins here on the leftmost atom, your rightmost atom, then it can hop to the second atom, to the third atom, to the fourth atom. What it means by charge not moving freely in an insulator is that for every electron that is a part of some atom in this lattice, in the insulator, the electron is going to always or be bound to that first atom. But if you know anything about quantum mechanics, or you've even seen the Niels Bohr model of the atom, right? Then you know that electrons are going around the nucleus in some way, shape, or form. And so what happens is, thinking in terms of quantum mechanics, is you get that for the positive charge here, as I bring the balloon closer and closer to the wall, the electrons remain bound to the atom, but the electron cloud drifts towards the positively charged balloon. The negative electron cloud comes close to the positive charge, meaning that the opposite side of that molecule now has net positive charge, and the close side has net negative charge. The charge remains bound, but you get a distribution that has regions of net charge on it. No, so the question was, is it like how electrons can jump energy states? No, the electrons don't have to jump energy states. It's just that the external electric field created by the balloon changes the shape of the actual cloud, not that it changes the energy state of the electrons themselves. It's just a shift, yeah. The beautiful models that you've seen where you've got like the S orbitals are going to be nice spheres and the P orbitals are those nice dumbbells and those kind of things. Those are done when the electron is isolated only with respect to the nucleus. But then if you bring in some sort of exterior field, all of that goes out the window. Get into, if you want to get into an interesting area of applied physics and chemistry, physical chemistry does exactly that. Like, how do all of these atomic clouds shift in the presence of other things? And how can that tell us how things are going to react? Okay. So a few things in terms of vocabulary, 14 minutes left. When objects are charged by being brought into direct contact with one another, we're said that they are charged by conduction. So go back to my previous thought experiment where I had two metallic spheres, one of them positively charged, one of them neutrally charged. When I touch them together and the charge distributes across them evenly, since I had said they were previously both conductors, then the mere fact that I caused those two to come into direct contact, those two spheres to come into direct contact, means that I charged the neutral object by conduction. Okay? Conduction just means direct contact charging. As it happens, it is possible to charge objects without ever bringing them into direct contact with one another. Because what happens in the atomic clouds, the electron clouds, can happen over the course of a conductor as well. That a conductor, the positive charge is going to distribute evenly over an isolated sphere, right? Because you've got all that positive, excess positive charge is doing its best to repel itself. So over a sphere, you get that net charge is going to distribute evenly over the sphere. I have +1 nanocoulomb. I expect that the distribution of that charge over the entire sphere is uniform. But now if I bring that positively charged sphere into contact, or not contact, into the presence of another sphere that's, say, negatively charged or positively charged, again, it can cause the distribution of that net charge to change. And we can work with that to charge things by induction. So this is an example of charging by induction. If I had a sub-figure 0 up there, it would just be the two metallic spheres, both showing that they themselves are neutrally charged to begin with. And this is charging by induction, that even though the two neutral spheres are in contact with one another, the thing doing the charging never actually touches the spheres. So what happens? Well, I bring the positively charged rod near the two neutral spheres. The positive charge is going to attract negative charge to the left, repel positive charge to the right. And if I bring those two spheres out of contact with one another now, even though I never brought the charged object into direct contact with these two, I end up with two spheres that began neutrally charged are now negative and positively charged, respectively. Never brought the thing, the rod, the positively charged rod, the thing with net charge, into direct contact with the spheres. Another example, if you're an electrical engineer, you're familiar with the idea of ground. Can someone tell me what ground is other than a convenient reference point for your voltage of a system? Yeah, it's a source or sink for charge. So we assume the Earth has nearly infinite charge, which is a good assumption for any circuit that we can build. And so you have a ground where, okay, if I need charge to move somewhere, I can dump as many electrons down that ground as I need to, or I can pull as many electrons up that ground that I need to. So again, if I had a sub-figure 0, it would be that this metal sphere here starts as a net neutral sphere. But then I bring the positively charged rod in, and it's going to give me a region of localized negative charge that's attracted here to the positive rod, and a region of net positive charge on the opposite side that is repelled. And if I attach the ground to the right-hand side of that sphere, well, that localized area of positive charge is going to want to rebalance to be neutral. The universe seeks net neutral charge. If you like Randall Munroe's XKCD comics, you might like his what ifs. And it's one of the what ifs is, what if we had a proton Earth and an electron moon? Or I should say a net where everything, there's zero negative charge on the Earth, all positive charge on the moon. And he talks about that much excess charge, even over those distances, would be enough to rip basically the entire universe apart. Right? Like the universe, most of the charges, the biggest charges we're going to work with are probably millicoulombs. A millicoulomb is a huge amount of charge because we're talking about many, many, many excess electrons. So I attach the ground here. Electrons come up the ground to neutralize this right-hand side here, but I still have to have a level of attraction. So maybe what you think of is these electrons are coming up the ground. Some of them stop here. The rest of them go to be attracted to this rod here. I disconnect the ground. So this is all left of the mouse, figure C. I disconnect the ground. And then in figure D by itself, I take the rod away. The negative charge redistributes itself evenly over the surface of the sphere. Again, I never touched the rod to the sphere, and yet I was able to charge the sphere even without ever touching it. Any questions about electrons, protons? Yes, right here.
If the rod, by conduction, if the rod touches the sphere, would the sphere be negative or positive?
So this is by convention of your textbook, this is a rubber rod. You might get some of the charge is able to drain off that rubber rod, but not much, if any. And so what should happen is some of the positive charge, if any, is able to come off that rubber rod, mostly by friction or something like that, you would likely end up with a positively charged sphere in that case. By conduction, if you actually touched the rubber rod to the sphere, it would have ended up positive, more than likely. Yeah, so the rubber rod is an insulator, and so it is unwilling to relinquish to move that charge around. Yes, Bill. How does the ground change things? Again, I would like to go back to the idea that was offered just a little bit ago, of that it's an infinite source or sink for charge, right? So that means I can pull up as much charge or dump as much charge up or down that ground as I need to, right? I'm not finished yet. I'm just laying out. But follow-up question?
Well, I was just basically, what's the difference between this picture and the last slide that didn't have the ground?
Here I had two objects. Again, a place where I could, two things that begin as one, but can become distinct, right? So that's the difference here. You don't have to have ground to charge by induction. Ground is just a convenient way to allow, really you do have a two-particle system. When conductors are connected to one another, you can't think of them as two distinct units, right? So this right here looks like two distinct metal spheres to us. But right now, because they're touching and they're conductors, they are one electric unit, right? But then I, by some Hulk power or something, am able to bring those two things apart. And they then, because they're no longer in contact with one another, they become two distinct units. Does that answer your question? Yeah. Okay. Grayson? Yeah. So let's think about this in reverse, or not reverse, but let's think about a different thought experiment. I bring the rubber rod into these two neutral spheres, and I leave them connected here such that the charge can move across this one unified unit. I leave the two metal spheres touching one another, and I take the rubber rod away. What happens? Yeah, now if I remove the rubber rod, I've removed this external charged element. The negative charge on the left sphere is going to be attracted to the positive charge on the right sphere. It's going to redistribute evenly. Then I break those two things into two distinct units. I had one neutral thing, and I broke it apart, and I end up with two neutral things. Okay, so how do we know that by bringing in the positive charge here, that the left one should end up negative and the right one should end up positive?
No, that the left will be attracted to the rod and not the other thing, the other ball. Because the other ball has a bunch of positive as well. So it gives the idea that if they're opposite, they attract.
Yeah, it all comes down to the fact that positive and negative attract one another. So across this one distinct unit, I have pulled electrons from the right here, actually from all over the place. I've pulled electrons because they are attracted to this rod. I've pulled them to the left side of this system, just based on the fact that the negatively charged electrons are attracted to the positively charged protons. Yep. It's a lot better to do in a lab. I would encourage you guys, whatever your physics labs looks like in Phys 2, we did this in lab, and it made it, rather than just a sequence, you can also find videos on it, rather than a sequence of images. It would make a lot more sense here. They are touching one another in part. No, they're just resting together. Yeah. Y'all have a great day. I'll stay in touch about class on Tuesday.